Hey, it's Mr. Shrum, and I'm back again with a physical science tutorial walkthrough, and we're going to talk about electrostatics. We're going to describe the types of charges, attraction, and repulsion of charges, polarization, and induced charges. All that will make sense in the slides ahead. So, for the introduction, you have probably experienced an electric jolt at some time. When you touched a doorknob, a car door, or some other metal object, a lot of kids use the trick of scuffing their shoes on a rug and then touching and zapping someone. I do that in socks. Uh, have you wondered how you can be zapped without being anywhere close to a live wire or a visible source of electric current, right? I've been shocked and there's nothing electrical around me necessarily. So how does that happen? Perhaps in elementary school or even middle school, you may have performed an experiment in which you rubbed a plastic ruler on cloth and then attracted small pieces of paper to the plastic ruler. We're going to learn about the natural processes that are responsible for this type of physical behavior. Lightning is a magnificent natural phenomenon. It occurs frequently, actually every day, and it's very impressive at night when it's very dark and you can see the charges in the sky. The power of lightning has been known to cause death and property damage because of electrocution or fire. A lightning storm is nature's most powerful display of electricity. Statistics predict that about 100 bolts of lightning strike the earth every second, and the sheer force of a single bolt can be as high as 1 billion volts. Lightning has fascinated the scientific community for centuries and continues to do so. A lightning storm is essentially nature's way of restoring the balance when there is an imbalance in electrical charge between the lower reaches of storm clouds and objects on the ground, including the Earth itself. In this lesson, we're going to explore how lightning and other related phenomena occur. To begin, watch this video about lightning and the science behind it. I cannot play the video in full, but I will kind of give you a brief rundown. But it's about static electricity and whatnot. Okay. I think that's just enough not to get a copyright strike. So let's move on to charges. Charges. You may have noticed times when your hair stands on end, such as when you take off a knit cap or even when you rub your head with a balloon. You may also remember rubbing a plastic ruler with a cloth in elementary school to attract little pieces of paper, like we said before. You could clearly observe a force of attraction between the paper and ruler. This attractive force must be stronger than gravity itself, because the little pieces of paper have to overcome the downward gravitational pull on them to rise up and stick to the ruler, right? You may have also noticed that the attraction didn't last very long. In a few moments, the pieces of paper fell off of the ruler. The Greeks noticed a similar attractive force when they rubbed amber with silk cloth. The Greek word for amber is electron with a K. So this force of attraction was called the electric force. So that's a fun fact. As you observed, the electric force does not require physical contact. So it's a non-contact force. Here you see a little baby in a balloon with his hair standing on end. Okay, so we're at the lesson activity, and it's kind of a do-it-yourself lesson activity lab almost. If you have a balloon and some type of sweater or sweatshirt, and you're going to rub the balloon against the fabric. And so you'll blow up a balloon, tie it at the knot, and then holding the balloon by its knotted end, bring it near the cloth item. And how does the balloon react to the cloth item? Well, if you do this, the balloon is attracted to it and it moves toward it. Attractive force. The balloon's behavior results from a change at the electron level. What do you think might have happened while rubbing the balloon and the fabric? Opposite charges attract each other. By rubbing against one another, the balloon and the fabric developed different electric charges, opposite electric charges, which caused the balloon to drift toward the sweater. Let me go back. C. Now take the same balloon that you rubbed against the fabric near a wall. What do you observe happening with the wall and the balloon? The balloon is attracted to the wall as well. Now for parts D, E, F, G, we're going to use the simulation for static electricity. I'll hide this meeting control. Okay, so for part D, the static electricity simulation, observe how objects accumulate static charges and how these charges interact. Select Show All Charges in the Charge Display menu, rub the balloon against the sweater, and observe the movement of charges and the change in the static charges on each object. Which charges are transferred in the simulation? How are the charges transferred? So, show all charges. Looks like the balloon is picking up negative charges, which are electrons. And the sweater, shirt is losing electrons. And now you see the balloon is attracted to the sweater. And it's also attracted to the wall. So negative charges move from the sweater to the balloon. What happens when the negatively charged balloon comes close to the positive charged sweater? The balloon experiences an electric force of attraction and sticks to the sweater. Move the negatively charged balloon away from the sweater and toward the wall. What happens to the positive and negative charges on the wall when the balloon comes close? So, okay. Pay attention to the way the charges move as you bring the balloon close. Looks like the negative charges move away from the balloon. The negative charges on the wall move away from the negatively charged balloon because like charges repel each other. Because the balloon has a lot of negative charge, if you put it against the wall, those negatively charged electrons move away while the positive charges stay where they are. When you bring the negatively charged balloon close to the wall, how do the two objects move with respect to each other? Explain this motion. Well, the balloon is attracted to the wall. Even though the wall is electrically neutral, it has both positive and negative, the negative charges in the wall move away from the surface near the balloon, leaving the wall surface with more positive charges than negative charges. These nearby positive charges affect the balloon more strongly than the more distant negative charges in the wall. And that's the end of that little lesson activity. To understand the interactions between balloons and sweaters, or the attraction between a plastic ruler and bits of paper, you need to consider the nature and structure of atoms. Atoms are made up of a positively charged nucleus. In this model, that's the nucleus, containing protons and neutrons, and negatively charged electrons that orbit the nucleus. These orbiting particles in this model are the electrons, we'll say. The law of charge interaction states that unlike charges attract each other and like charges repel each other. When a balloon rubs against a sweater, the electrons on the surface of the sweater rub off onto the balloon. The loss of negatively charged electrons leaves the sweater with a slight positive charge that attracts the negatively charged balloon. The net charge that accumulates on a stationary object is known as static electricity. Unlike the electricity that flows through wires to power our homes, schools, and offices, static electricity is static. Its electric charge accumulates and is confined to one place. So static, stationary, it's not moving like how we really think of electricity flowing. In that simulation, you saw that a negatively charged balloon could somehow be attracted to a completely neutral wall. In this case, a few of the electrons in the wall were able to migrate away from the negatively charged balloon, but the wall's positive charges, static atomic nuclei, were stuck where they were. As a result, the surface of the wall became more positive than negative, and the negative balloon was attracted to it. Similarly, in a lightning storm, colliding particles of rain, ice, or snow create an electric imbalance in the atmosphere. Objects on the ground, such as buildings, trees, and even people, become positively charged. The lower reaches of the storm clouds acquire a high negative charge. These opposite charges are naturally attracted to each other. This static charge attraction is finally overcome when the atmosphere ionizes rapidly, creating a channel for electricity to be transferred through the air. That's what we call lightning. Energy and the separation of particles, separation of charges, excuse me. Energy and the separation of charges. The molecules in the matter that surrounds you are typically electrically neutral objects. That's why your pen is not usually attracted to your book or your shirt. Rubbing, however, often causes a transfer of charge and a display of static electricity. You may have noticed this when brushing your hair or a pet's fur. Suddenly the hair is sticking up all over and attracted to the brush. When two neutral objects rub against each other, the friction between them can overcome the binding energy between the electrons and the nuclei of the atoms on the surface of the object. This may cause electrons from the outer orbits of the atoms to escape from their nuclei. The loss of these negative electrons causes the object to become positively charged. The mobile electrons, in turn, migrate onto another object, causing it to become negatively charged. As a result, one object is left with an excess negative charge, and the other object ends up with an excess positive charge. Here's a cute little kitty. All right, so checkpoint question, testing whether you're following along. In a lightning storm, a large negative charge accumulates in the lower regions of low-lying clouds. Which term best describes this charge? We're going to say static electricity. The charge that accumulates in the lower regions of the clouds before a lightning storm is stationary or static. Benjamin Franklin. For centuries, human beings have gazed at a stormy night sky and been captivated by the claps of thunder and bolts of lightning. In 1752, the American scientist, statesman, and author Ben Franklin discovered that lightning is a form of electricity. As a lightning storm was about to break, Franklin flew a kite with a stiff wire attached. He tied a metal key to the other end of the string and let it hang close to a Leyden jar that was used to store electric energy. As the rain wet the string, electricity from the atmosphere traveled down the wet string and jumped into the jar in the form of sparks. Franklin thus proved that electricity and lightning were the same thing. Franklin is also credited with naming electric charges positive and negative. In the late 19th century, so late 1800s, the physicist J.J. Thomson discovered that electricity was composed of negatively charged particles called electrons that came from within atoms. The final piece of the puzzle was solved by Ernest Rutherford, a student of Thomson's from New Zealand. Between 1909 and 1911, Rutherford discovered that the atom contains a nucleus at its center that has a positive charge and a mass that constitutes nearly all of the atom's total mass. The positive nucleus is orbited by much lighter electrons. And here's Ben Franklin. Here's a sodium atom, neutral, loses an electron. That sodium ion being a charged particle. So when an atom loses an electron, sodium is now an ion, and then there's this free electron. Neutral objects have an equal number of positive protons and negative neutrons. They cancel each other out, balanced. The charges within them are balanced, so their net charge is zero. Atoms themselves are electrically neutral, with the charge from electrons balancing out the charge from protons. However, the addition of energy can cause the outer electrons of an atom to escape from the atom. When this happens, the atom ends up with a net positive charge. It takes a fairly small amount of energy to remove an electron from some atoms, such as sodium. As a result, sodium is often found as a positively charged ion. Electrons can also migrate from atom to atom within an object and even move from object to object. An object that gains electrons acquires a net negative charge because the number of negatively charged electrons exceeds the number of positively charged protons in its atoms. From a subatomic viewpoint, an object acquiring a charge is simply a process of its atoms gaining or losing electrons. It's important to note that in a system where electrons are transferred from one object to another, such as in a chemical reaction or a physical transfer of electric charge, the combined total charge remains constant. According to the law of conservation of charge, individual charges can be neither created nor destroyed. A transfer of electrons can cause only the separation of positive and negative charges. Substances have a tendency toward stability, so they will generally interact with other substances to move toward electrical neutrality. When a positively charged object comes close to a negatively charged object, electrons will jump between them until the two objects are brought closer to a state of electrical neutrality. On the atomic scale, some atoms, such as sodium, have a tendency to become positive, while others, such as chlorine, have a tendency to become negative. These two elements reach overall neutrality, however, by joining together to form sodium chloride, and that is a neutral substance. We have explored the interaction of positive and negative charges when a plastic ruler rubbed with cloth is brought near neutral pieces of paper. The paper is attracted to the ruler. Here, a neutral object is attracted to a charged object. How can that be? Recall that an atom consists of positively charged protons and negatively charged electrons. While the protons are held tightly within the small nucleus, the electrons move freely in the vast free space outside the nucleus, known as an electron shell or electron cloud. So we have this tight nucleus, and yet around it there's this cloud, a shell of electrons that are moving all over the place. In certain elements, the electrons in the outermost shells are very loosely bound and can be induced to move within the object. If a charged object is brought close to these loosely bound electrons, the electrons are induced to move toward the object if it is positively charged and away from the object if it is negatively charged. You'll learn more about this phenomenon later in this lesson. Recall how a balloon acquires a negative charge when it is rubbed against a sweater. When a negatively charged balloon approaches a neutral wall, the electrons in the wall are repelled by the negatively charged balloon. The electrons closest to the negatively charged balloon will experience the greatest repulsion. The loosely bound electrons will be induced into moving away from the balloon, but the positive atomic nuclei stay in place. This movement of electrons from one side of an object or one end of an object, in this case the wall, to the other side leaves one side with a positive charge while the other side becomes more negatively charged. When this separation of charge happens within a neutral object, we say the object has been polarized. The process is known as polarization. As a result of this polarization, the negatively charged balloon in the simulation was attracted to the wall. Although the wall was neutral, the surface closest to the balloon had a net positive charge. When a glass rod is rubbed with a silk cloth, it develops a static electric charge. Glass is a substance that readily surrenders its electrons with the addition of energy. Because the glass loses its electrons when rubbed with cloth, it becomes positively charged. Silk, cloth, on the other hand, does not surrender its electrons as easily as glass. Therefore, when a glass rod is rubbed against silk cloth, it is able to transfer electrons to the cloth, giving the cloth a negative charge while the rod itself acquires a positive charge. Similarly, when a plastic comb is rubbed against silk cloth, it also gives up electrons, although not to the extent that glass does. The plastic comb then acquires a net positive charge. The plastic comb and the glass rod, when charged, are both able to attract pieces of paper. Although electrically neutral, paper is drawn toward the charged objects because the paper becomes polarized. The electrons in the atoms of the paper are attracted to the positively charged objects and move slightly within the paper toward the positive objects. Thus, the side of the paper facing the charged rod becomes negatively charged, while the far side acquires a positive charge. All right, so checkpoint question. A balloon is rubbed against a wool sweater that tends to lose electrons. Another balloon is rubbed against a silk scarf that tends to gain electrons. What will happen when the two balloons are brought close to each other? So we have one that has been rubbed against a sweater. Another balloon is rubbed against a silk scarf that tends to gain electrons. We will have one balloon. The first balloon gets negatively charged from rubbing against a wool sweater. And then the second balloon is positively charged. So they're going to attract each other. And we'll pick this up later to learn about conductors and insulators. But that's it for this lesson right now. And until I see you guys, have a good day/week, and I will see you all later. Bye-bye.